not 9.4, because we haven't have covered it at that point yet. All right, so 9.1 is going to be logarithms and logarithmic functions. So, let's talk a little bit about what a logarithm is. Before we even really get into it, I just want to kind of give you something to think about. So this is not on the notes or anything like that. This is just a conceptual understanding of what a logarithm is. Okay, so logarithms are inverses of exponential functions, and I'm going to show you why that is. So if I said 2 to the x power is equal to 8, you would tell me x would have to be what? 3. You just use deductive reasoning to figure that out, right? And that's great. You can sometimes do that. But here's where we pose a problem. What if I said 2 to the x power equals 0.32, or maybe 31? What would you guys tell me? Would you be able to figure that out in your head? No, but you probably can think of the fact that if I can figure out what x is for this one, there probably is a way to figure this out, right? You just don't know it yet. Okay, there is a mathematical way for us to do that. And that's where we use something called a logarithm. Okay? So we're going to be learning about logarithms over the next few days. We tried to make it in a digestible way for you guys, so we're not going to talk about all of the skills and topics of logarithms just today. We're just going to kind of dive into the notation today more so, and some of the basics. All right. So, a logarithmic function will always have an inverse of an exponential function. And the reason that's important is the exponential function allows us to graph the logarithmic function and then flip the table values to graph its inverse. Okay, because if we ever want to graph the inverse of something, we can simply flip the x's and the y's. That's the definition of an inverse, which you guys learned about in Unit 6, I believe it was. So this is the standard form of the logarithmic function, a, h, and k. You're all familiar with a, h, and k by now, right? That's, vertical stretch, vertical compression, and reflection. Left, right, but opposite, and then up, down. Same goes for these types of functions. Now, with logarithmic functions as opposed to exponential functions, the h determines the asymptote instead of the k because it is a vertical asymptote instead of a horizontal one. This is what an exponential decay as a logarithmic function looks like, and a growth. So, let's go ahead and get into one of the graphs. So like I said, today we're going to be focusing very heavily on understanding the notation more than anything, because I believe if you don't understand the notation, you really can't get very far with these, so we're going to practice a lot of that. So, this is log base 5 of x. So it's a function, that's how you say it, log base, whatever it is, of x, okay? Now, if your logarithmic function doesn't have a base, you assume the base is 10. Just like with, if you don't have an exponent, you assume it's 1. That's a rule of logarithms, all right? So, in this case, what we're going to do, instead of trying to graph the logarithmic function, which we don't know how to do yet, we are going to graph its inverse. So to find its inverse, it's going to be whatever the base is to the power of x, okay? So we're going to start by graphing its exponential inverse, because I know you all know how to graph exponential functions. Now, not necessarily graph it, we're going to make a table for it, okay? We're going to make a table for it. So, step 1 is we're going to make a table for that exponential function. So we're going to plug those values into the exponential function to get their outputs. So, 5 to the negative 1 power is 1/5. 5 to the 0 power is 1. What's 5 to the first power? Good. Now, we know that these two functions are inverses of each other. Okay, if you want to write that, they are inverses of each other. So inverses have the property that you can flip the table to find the graph of the other. So it's a tool to help us get the graph of the logarithmic function without knowing how to graph a logarithmic function. Now we're going to graph the new table that we just came up with, 1/5 negative 1, 1, 0, and 5, 1. And my points are going to look something like this. Now with any logarithmic or exponential function, before you start connecting the graph to see what it looks like, it's useful to first find its asymptote, okay? So here's the rule. The asymptote of a logarithmic function, I'm going to say that all the time, is x equals h. Now the reason I'm so weary to tell you guys that is for this reason. H is always the opposite, okay? So if this has an h in it, if it's like x minus 2, it's x equals 2, okay? So just be mindful of that when you're doing that, that it's going to flip, all right? And you can kind of see that in the graph as well. Now, if I draw or write the logarithmic parent function, like right here, you guys can probably see, do we have an a here other than 1 in our graph, our equation? No. Do we have an h other than 0? Do we have a k other than 0? No. So this actually has no transformations. Okay. Now, that is going to help us determine our asymptote as well. So what would our asymptote be here if we don't have an h? H equals 0. X equals 0 is the same thing as the y-axis, okay? So this is the line, x equals 0, all right? Now, to graph this, we're now going to graph it just like we do with an exponential function. It's going to curve around the asymptote. So logarithmic functions have vertical asymptotes, exponential functions have horizontal. Yes? Because you can see there's nothing added or subtracted from the x on there. All right. So, like I said, these are inverses of exponential functions, so a lot of the properties are shared or flipped in some way. So, we learned about exponential functions, and exponential functions always have a domain of all real numbers. So, what do you think this one has? Not a domain of all real numbers, but a range of all real numbers. And you can visibly see that because range is up and down. As you can see, this goes down forever, and it also is going up forever. It's just a little slower, but it's still going up forever, okay? Now, as for our domain is going to be bound by that vertical asymptote, right? So, is my graph ever going to approach negative infinity over here? No, the closest it gets to that is 0. But we don't actually touch 0 because it is an asymptote. Good. So just be careful of that. Make sure you don't put a square bracket here. It's got to be curved, okay? Now, on this direction, going to the right, we approach positive infinity. Because remember, domain is left, right, range is up, down, or down, up. And behavior is based upon your domain and range. X, like we said, it never approaches negative infinity. The closest it gets to that is approaching 0. And as it approaches 0, what is my function doing? Good, it's going down to negative infinity. As my graph goes to the positive infinity direction for x, what's my function doing? Going positive. Now, for the parent function on this, I'm going to write it down here so I have more room. Anytime you have no transformations, your parent function is always just whatever your original equation was, okay? So a parent function is where we take the equation and we remove the transformations. But as you can see, there were no transformations to remove. So it's just, parent function is the function itself, okay? So does anyone have any questions about that? All right. Yeah, go ahead. Sorry, were you saying something?
What was the asymptote, whatever the a was?
Oh, it's just x equals 0.
Okay.
Any other questions? Okay. All right. So this one here we're looking at is a little bit more complex. It's not difficult, but it just has a few more moving parts to work through here. So first thing I'm going to do is I'm going to write the logarithmic parent function above it. That just helps me visualize what kind of transformations I have. So sometimes writing it there can help you see if we have an A, we have an H, we have a K, what's happening. So do we have an A in this one? No, it's just 1. Do we have an H? An H of 1, right? Which tells us my asymptote is x equals 1. Because remember, why is H positive here? It's always the opposite. Okay? Whenever a formula has a minus sign in it, you know that value is always going to be the opposite. That goes for any math that you take. Now we can identify the transformations. We know that H goes left and right, but because it's minus, it's going to the right. So we know it's going to go to the right 1. And then we know it's also going to go Up, 2, good. K is always up, down. All right, so now that we've identified all of that, we're going to go ahead and graph it. Now the way that we're learning to graph it today is via inverse rules, okay? So we know that this particular parent function, so we know that the parent of this log function would be this. Everybody see why that's the parent? It's the function with its transformations removed. Does everybody see that? So then from there, we know that this is its exponential inverse counterpart, okay? The inverse is always going to be whatever the base is of the logarithmic function to the power of x. And you can always graph that, flip the table, and graph your logarithmic function. So now we're going to go ahead and graph this. So 1/2 to the negative 1 power is 2. If you don't believe me, you can try it in the calculator, I promise. What's anything to the 0 power? 1. What's 1/2 to the first power? 1/2. Good. Now you can just flip the table. And just to be really clear here, what we're doing right now, this table that we're graphing, this is not the actual function. We are graphing the parent function, okay? So we're going to start by graphing the parent function. Notice that this does not have those transformations in it. So what I'm graphing right now is not the final answer. So we're going to start by graphing it. We have 2, negative 1, 1, 0, and 1/2, 1. Now, before we actually connect this graph, we know we have to find our asymptote. Anytime you're graphing a parent function with all of the transformations removed, we know for a fact that it's always going to have an asymptote at the y-intercept, okay? Because, of course, the h is just 0. That's the reason for this. So, yes, go ahead.
I thought h was 1.
So like I was saying, we're not actually graphing the function right now. We're just graphing the parent of it. So we're not graphing this. And you're right, h is 1 in the actual function, though. So right now, we're just graphing the parent. So this is actually not the graph that we're actually looking for. And you're going to see that in a second. I just want to make sure that this doesn't look like it's going straight. It's going downward. All right, so Jack brought up a point about how this doesn't have the same asymptote as the actual function. So we're going to talk about that now. So we just graphed the parent function, and that's great, but we know that's not the same thing as the actual function. Okay, so I just graphed the parent. Now I'm going to graph the actual function. So the actual function is the same as this function, except for it's been shifted right 1 and up 2. So what we can now do is take this particular graph and shift it right 1 and then up 2. So right 1, up 1, 2. Right 1, up 1, 2. Right 1, up 1, 2. Everybody got that down? Okay. Guys, you shouldn't be on your phones right now. You should be getting your notes down, okay? Thank you. So we have this graph. Now, we know that this particular graph, like Jack said, has an asymptote at what? 1. So we can draw our new asymptote in. Just like that. So just to be really, really clear to everybody, this one in the yellow is the one that we actually care about, okay? The other graph is just a tool to help us get the graph we actually want. Does that make sense to everybody? So we're going to be analyzing the one in the yellow. We don't care about the other one anymore. It just helped us get the one that we actually want. So the domain of this particular one is from 1 to positive infinity, right? The range is all real numbers. All of these log functions will have a range of all real numbers. The domain will always be based on the asymptote. And then in behavior, as we approach 1, because we never approach negative infinity, our function is going upward. Good. As we approach positive infinity, my function is going Slowly it's going down. Good. And the parent function is the one we just graphed. Y equals good. Log half x. So a lot of times in more complex math, we start by graphing the parent and then adjusting those transformations to find the new function so it's easier. Yes?
Do we put the domain and range as an inverse or the
So when you analyze the domain and range, you only are ever going to do it for whatever that actual original function is. All those other tools we use to get us there, we're not going to analyze those. Any other questions? Okay. So now we're going to talk about some conceptual things with logs and all that stuff. Okay. So all types of log expressions. Oh, okay, thank you. You guys need the notes? Yep. Right here for you guys. Go ahead. So all types of logarithmic expressions and equations can be represented as each other. So I can rewrite a logarithmic equation as an exponential one or vice versa. Okay? So here's how we do it. So from log to exponent, I use something called the arrow rule. Base to the power of 2, whatever it's equal to, is equal to 16. So that's how you convert a logarithmic expression to an exponential one. Now I just want to be really, really clear with you guys today. Yes, there is an actual application for this. We're not going to talk about it in depth today. We're getting to it. We're going to progress into it. So don't worry. You'd be like, what's the point of this? We'll get to that. Okay. Today is just about learning the notation, so you're not overwhelmed by all the steps. All right. So using that same procedure, what would the next one be? Good. 3 to the 6th power is equal to? Good. 729. And those are both true statements. Okay. So that's how you convert a logarithmic to an exponential. So a log is a tool to help us solve for missing exponents. We're just now learning how it operates. Okay, the procedures, the comparisons, all that stuff. All right. Now we're going to go backwards. We're going to go from exponential to logarithmic. So here's how you do it. It's going to be log whatever your base is going to be your base of your log as well. Then it's going to be what it's equal to. Equals the power. And if you ever get stuck, you can use the arrow rule to check it back. You see what I'm saying? So I can go, oh, that does work. It gets me back to what I started with. Does everybody see that? What would be the next one? Log 125 of 5 is equal to 1/3. So remember, logs represent exponents, so they're going to be equal to exponents. They're always going to be equal to the exponent. So that's the rule. Now, sometimes you're going to be left with a logarithmic expression. What's the difference between an expression and an equation? Yeah, it doesn't have an equal sign in it. So these are expressions. Now, we can convert these into equations by setting them equal to some variable. Okay, you can pick any variable you want. Now, there's many different uses for this. This is just a tool to help you solve it. So now you're going to do the arrow method that we just learned about. 3 to the x power is equal to 81. 3 to what power would be 81? 4. Because 9 squared is 81, and 3 squared is 9, so 3 to the 4th power is 81. So all of these ones that we're going to be doing are ones that you could like logic your way through, trial and error. You're going to learn ones that don't work like that in the future. Okay, so they don't always have to work like that. Come on up, get missing notes. All right, so the next one we're going to set it equal to a random variable. Okay. So it's going to be 1/2 to the power of x is equal to 256. Now we can use some of those rules we learned about in the last chapter or unit to figure this out. Anybody remember how we can rewrite 1/2? You're close. negative, not negative 2, but
Oh, 1 to the
yeah, you guys are all saying parts of it. It's 2 to the negative 1 power, right?
oh,
Would be the same thing as 1/2. Because when you want to bring something up to the numerator, you can put it to the negative 1 power. Now, how could we rewrite 256 so it has a base of 2? To the
divided by 2.
256 to what power? Or sorry, 2 to what power is 256? Any guesses? Bigger than that. So 2 to the 5th power is 32. 2 to the
8.
Very good. 2 to the 8th power. So this is one of those things you got to kind of trial and error. Okay. Now, what's the rule? If we have the same base, what can we do with the exponents? Set them equal to each other. So negative 1x is equal to 8, which means x equals negative 8. So like I said, these like just are all trial and error ones, but there is a way to do it mathematically as well in the calculator, which we learn about. All right. Next one. What do you notice my log is missing here? A base. So what did we say the implied base is? 10. Now that you put in the implied base, you're going to set it equal to a variable. You can also use like y or z. So what would x have to be here? 2. So what that means is this is equal to 2. So if you did it in your calculator, which you'll learn about, it's going to come out to be 2. I'll just use y to change it up. 9 to the y is equal to 1 over 81. Now, I know that I could rewrite this like this, right? Does everybody agree with that? Now, I want to bring that up. What can I do with it? Make it negative. So y is equal to negative 2. Okay, negative 2. So that's how you can go about doing it. Come on up, get a thing. You guys can just toss the passes for testing. Thank you. All right. Do we have any questions? Okay. So now we have one word problem we're going to do. It's not too bad, though. So it says the formula represents the change in the f-stop setting. So this is the f-stop setting used in less light, where P is the fraction of sunlight. Okay? Just P. So it says here, Benito's camera is set up to take pictures in direct sunlight, but it is a cloudy day. If the amount of sunlight on a cloudy day is 1/4 as bright as direct sunlight, how many f-stop settings should he move to accommodate less light? So what letter does this number represent here? P. So P is equal to what? 1/4, right? Now that we know what P is, what can we do with it in the formula? We're going to plug it in, right? To the formula. Everybody see what we did there? What is 1 divided by 1/4? If you do it in the calculator, it'll tell you what it is. Keep, change, flip, it's going to be 1 divided by 0.25. It's 4. So it's 4. Okay, that's just if you do 1 over 1 times 4 over 1, keep, change, flip. So if this ever gets, your setup ever looks like this, you can just flip it around. And now, don't we have a problem like we just did on the last page? So it's going to be 2 to the what? Equals 4. So n equals what? 2.